here we go. Try number 3 for learning target 10. So learning target 10 is going to cover Gibbs free energy, which will allow us to decide whether a process or reaction is spontaneous or non-spontaneous at a particular temperature. So let's review what we mean by spontaneous processes. We saw this in learning target 9, but this will be a brief review. Spontaneous processes are processes that will continue on their own without outside intervention. So for example, if I set a ball on the top of a ramp and release it, it will roll down the ramp on its own, thereby being a spontaneous process. If I am burning wood, once I added enough thermal energy to get that wood to catch on fire, the fire will keep on going until it's out of fuel all by itself. Therefore, burning wood is a spontaneous process. And then when we did our enthalpy lab, where I added the zinc to the copper sulfate, as soon as I added that zinc to the copper sulfate, the reaction ran on its own without outside intervention, and thereby being a spontaneous process. So all 3 of these processes happen to be exothermic, meaning heat was released from the system out into the surroundings. Even the balls rolling down the ramp was an exothermic process because some of the kinetic energy that was contained in the balls was being transferred into thermal energy by the friction being applied to the balls from the ramp. So these are all exothermic processes. We can have spontaneous processes that are also endothermic as well. Let's look at melting ice. If I sit an ice cube out into a room that's room temperature, the ice will spontaneously melt by itself. However, this is also going to be considered an endothermic process because heat is going to be leaving the surroundings and entering the system, where the system is going to be the ice cubes, the surrounding is going to be the room. This is going to be an endothermic process, so it's going to have a positive enthalpy. But it's still spontaneous because the ice will just melt due to the temperature of the room. Let's look at some non-spontaneous processes now. So a non-spontaneous process is a process or reaction that requires a constant input of energy to proceed. So let's pretend I take an ice cube and I sit it in a room that's room temperature. There's no chance that this is going to happen. There's no chance that actually if I have a pile of water to start, that water is going to reform into an ice cube. There's just too much entropy present in the water because the particles are all over the place, and it's just statistically improbable for all those water molecules to reform into a solid lattice structure. So this is going to be a non-spontaneous process. Water will not spontaneously freeze at room temperature. This is a video running in reverse. So ice freezing at room temperature is definitely a non-spontaneous process. So when I throw a sugar cube into tea, that sugar cube is going to spontaneously dissolve into the tea. But to remove that sugar cube from the tea would be a non-spontaneous process. The reverse reaction would be non-spontaneous because I would have to decrease the entropy from a liquid phase back to a solid phase, and I would also have to put tons of energy into that tea to put every single sugar molecule back together to pull out the sugar molecule. So removing dissolved sugar from tea is definitely a non-spontaneous process. Here's another non-spontaneous process, and we're going to refer to our atmosphere for this example. Our atmosphere is 70% nitrogen, 20% oxygen, and 10% other stuff. And we're really fortunate as human beings that the reaction of nitrogen gas plus oxygen gas will not immediately make nitric oxide, because this is something that's poisonous to human beings. I can make this happen if I have a constant input of energy to proceed, if I input a high temperature to the mixture, or if I increase the pressure dramatically. But this is just not going to happen on its own at standard temperature and pressure. Fortunately for us, so we can breathe. So this is what our atmosphere would kind of look like. We've got a mixture of oxygen, we got a mixture of nitrogen. They each have their own partial pressures. And then the homogeneous mixture of oxygen and nitrogen would just be the spreading out of oxygen and nitrogen particles in with it, between each other. The pressure here says 752 millimeters of mercury. That's basically standard pressure, like 1 atm. Now, this is also an endothermic process. So notice with this process here, with my enthalpy time graph, the energy of the reactants is lower than the energy contained in the products. And chemical compounds are a lot like humans. They want to be at the lowest energy state possible. So this is not a favored reaction when you've got more energy in the products than you have in the reactants. The reactants, nitrogen and oxygen, have a huge amount of energy to overcome before they finally release a little bit in order to become the products of nitric oxide. The overall energy in the products is greater than the reactants, and therefore the enthalpy is positive. And I'm bringing this back up because of some questions that came up on Learning Target 4 through 6. When you have more energy in the products than you do in the reactants, it's an endothermic process, and delta H will be positive. So non-spontaneous process with an endothermic process here. So how can we use enthalpy and entropy to predict spontaneity? So I'm going to show you this reference table. And I would recommend, before you hear the explanation, pausing the video at this point to copy this table or screenshot and print out this table to have in your notes. After you do that, I will explain to you why each one of these rows are numbered, because each one of these rows has a particular example. So pause the video at this point, figure out how to copy down this table. All right, hopefully your table is copied down. Let's look at row 1. And my example for row 1 is, again, wood burning. So when I burn wood, the enthalpy will be negative because heat is leaving the system and going out into the surroundings. The entropy is going to be positive because I'm increasing the number of arrangements that the particles can take. I'm making a gas with the carbon dioxide, carbon monoxide product that I'm creating. The ash is going all over the place. Entropy is increasing. So if I've got a negative enthalpy and a positive entropy, this reaction is going to be spontaneous at all temperatures, meaning that as soon as I get this wood to start to burn, it's going to burn whether it's cold outside or whether it's warm outside. It is going to be a spontaneous process. Example number 2, back to my melting ice cubes. So melting ice cubes is going to be an endothermic process because heat is leaving the surroundings and going into the system. So my enthalpy value is positive. My entropy value is also positive because I'm going from a solid to a liquid, so I'm increasing the number of arrangements possible. And so we can say here that this particular system is going to be spontaneous, but at high temperatures. What do we mean by high temperatures? Don't know quite yet, but we're just going to bookmark that for a second. So if the temperature is high enough and enthalpy is positive, entropy is positive, the reaction will be spontaneous, dependent upon the temperature. Same here with number 3. Number 3, we're going to look at the exact opposite. We're going to look at a negative enthalpy value, so it's going to be an exothermic process again. So freezing water into a snowflake is an exothermic process because heat is leaving the water and going out into the surroundings because the water is freezing. You've got a decrease in entropy because I'm going from a liquid to a solid. And so if I've got a negative enthalpy, which is going to be exothermic, I got a negative entropy, it's going to be a spontaneous process if the temperature is low enough. Water has to be at 0 degrees Celsius or lower for this to happen, so that's the only time that this will be spontaneous. So again, we don't know the definition quite yet of low, but we're going to figure that out on the next slide. And when something is never spontaneous, here's my sugar in tea example again. In order to make the sugar back into a sugar cube, I'd have to put a lot of energy back into the sugar particles to pack them all back together. So that would be an endothermic process. I would be decreasing the entropy. I'm going from a lot of chaos to not so much chaos. So my entropy would be negative. So endothermic with a decrease in entropy, that will never be a spontaneous process. The reverse would be spontaneous, but not the forward direction. So trying to pack back that sugar after it dissolved in tea, not spontaneous. So keep this table handy, and we're going to explore what we mean by high and low temperatures. So, review again. Enthalpy is going to talk about the flow of thermal energy in and out of a system. The entropy measures the amount of random energy there is and is temperature dependent. So I'm going to talk to you about how these two are going to relate to each other to figure out if a process is spontaneous or not. If I take the enthalpy of a system, the amount of heat energy flowing in and out, I subtract from that the randomness of the particles at a particular temperature, we can calculate what we call the free energy available to that system at a particular temperature. And if I can get that value, I can tell if that process is going to be spontaneous or not. So let's put this all into a formula. And the formula is going to be the Gibbs free energy formula, which is denoted with the capital G. It's the amount of free energy available to a system in terms of temperature if pressure and volume remain constant. Here's what that equation looks like. I would definitely pause the video at this point and write this down. The change in Gibbs free energy is going to be equal to the enthalpy of the process, the change in enthalpy of the process, minus temperature times the change in entropy of that process. And here's my variables denoted. G is Gibbs free energy, capital H is enthalpy, T is temperature. Notice that I got to be careful with units here. Temperature here is in kelvins, and so if I give you a temperature in Celsius, make sure you add 273 to get kelvins. And the entropy values you're going to find in your data booklet are going to be in joules. So to solve this equation and make sure all my units match, I'm going to have to convert joules to kilojoules. So pay attention to that. So pause the video, write down this equation, highlight it. That's a really important equation. If you get your data booklet, if we have exams, that equation will be in your data booklet as well. So what does that value actually mean? So if I solve for Gibbs free energy, and the change in Gibbs free energy is negative, we say the reaction is spontaneous in the forward direction, written out in chemical equation from left to right, and non-spontaneous in the opposite direction. So for example, burning wood is going to be spontaneous. So when the wood burns, it's the spontaneous way. If I took all the ash and carbon dioxide, carbon monoxide, try to pack it back together again to make the wood before it burned, that would be non-spontaneous. So in the forward direction, delta G is negative and the reaction is spontaneous. If the change in Gibbs free energy is equal to 0, the reaction is at equilibrium, which means there's no change in the concentration of the reactants in the products. If delta G is positive, then the reaction is going to be non-spontaneous in the forward direction, but the reverse will be spontaneous. So for example, if I had liquid water and I wanted at room temperature to put it back together to make an ice cube, that is not going to be a spontaneous process, and delta G would be positive. But if I took that ice cube at room temperature and melted it, it would be spontaneous and delta G would be negative. So moral of the story is this: G negative, spontaneous; G positive, non-spontaneous; G 0, everything's at equilibrium, no longer changing. There's one more rule attached to this, and that's this one. Just like enthalpy of formation of elements, we assume that they've always been here, so they've always been formed, so the enthalpy is 0. We assume that the change in Gibbs free energy of elements is also going to be 0, because the state of matter of those elements at standard temperature and pressure are not going to change. So if I'm doing a calculation with elements, delta G will be 0 for those elements, just like the enthalpy of formation. Okay, so in the next video, you're going to see some example problems with this. Keep your notes handy as we work through the example problems, and I will see you in the next video.